The multiplication rule, which is also called the product rule, states that the probability that two or more independent events will occur is equal to the product of their individual probabilities. Okay, so a couple of important things here. What we're looking at is going to be independent events. So this independent event means that one of them has no influence on whether the other event is going to happen. So we have a couple different events. We'll have event A and event B. And so what we're saying is that if we wanted to know what is the probability that A is going to happen, and I'm going to write and here in red because this is going to be a key word here. If we want to know the probability that A and B, which don't influence each other, that both of them will occur, what we want to do is look at the product of their individual probabilities. So we're going to end up multiplying the two together. So we will figure out the probability of A, and then we'll figure out the probability of B, and we'll take the two, we'll multiply them together, and then we get the probability of both of them occurring. Now, the reason this is important is because when we do start to talk about genetics, the multiplication rule can be applied quite often. So ways that we will use this when we start to talk about genetics is going to be that we use this a lot when we look at subsequent offspring. And what we mean by subsequent offspring is that the first child does not impact what the next child is going to be, or the genotype or phenotype of the first child doesn't affect the next. So each child or each offspring is an independent event. And we are looking and talking about independent events here. We'll also use this when we're looking at multiple genes at a time, because each gene is inherited independently. And this is based on Gregor Mendel's law of independent assortment. Now, we will find later that there are certain genes that don't assort or get inherited independently. But for now, we're going to consider all separate genes to be considered independent events, meaning they will get transmitted to the offspring independently from each other. So if we go through an example where we're talking about this idea that each offspring is an independent event, one of the easiest things to start out with is just if we think about boys versus girls when we're looking at the sex of an offspring. So this is something we're pretty familiar with. We understand that if you're going to have a child, there are two possibilities. So we expect that half of the time you're going to get a girl and half of the time you're going to get a boy. Okay, so we say 50-50% chance. So if we're having two children and we want to know what is the probability that both children are going to be girls, then what we have to consider is that it really doesn't matter what happens the first time or whether we have a girl or a boy the first time. That next time, the second time we have a child, that is an independent event. It's a separate conception. And so we are going to use the multiplication rule for this. So what we would do is we would look at the first child first. So we would say, okay, what is the probability that this first child is going to be a girl? And we just looked over here and we said the probability that a child is going to be a girl is really just a half. And so that's the probability of our event A. And then if we wanted to say, okay, what is the probability that the second one is going to be a girl? Well, if we look at that one kind of as a standalone event, the probability that the second one's going to be a girl is also 1/2. So all we would do here is we would take these independent events, because we want this one and this one, and we multiply them together and we get an overall probability of 1/4. Okay, so if you have two children, you have a 25% chance or a 1/4 chance that both of those children are going to be girls. Now, if we looked at just another variation of this, we could look at more than 2 children at a time, or we could look at getting maybe the first one being a boy, the second one being a girl, and then maybe we want another boy at the end. So every time we look at those multiple children, each one is, again, an independent event. We would evaluate the probability of just that one child being the boy or the girl or whatever we're looking for. And then we would move on to the next child, evaluate its probability, and then the next. So if we alter this question and we want to say, what is the probability of getting or of having a boy, and then we'll say a girl, and then a boy, and another boy. And we're going to add to this in that order. So in other words, we want the first child to be a boy, the second child to be a girl, the third to be a boy, and then the fourth to be a boy as well. So if each one of these is an independent event, we say, okay, first of all, what is the probability that that first one's going to be a boy? It is 1/2. Then we would look at the second child, and we would say, what is the probability that this second one is going to be a girl? And that would be 1/2. We'd look at the third. We're going to get 1/2 for its probability of being a boy. And then when we look at the fourth one, the probability of that one being a boy is going to be 1/2 as well. So if they're all independent events, we go across and we multiply. And in this case, we're going to get 1/16. So if you have 4 children, then there is a 1 in 16 chance that the first one will be a boy, second one a girl, third boy, and fourth boy. Okay, so that's just looking at just boy versus girl in our offspring. Now we can take this same idea and we could apply it to a very simple genetic cross. So let's do that next. So let's assume that we have this particular cross that we're looking at, and we're asking the question, what is the probability that I'm going to say the first offspring is going to be big A, and the second offspring is going to be heterozygous. Okay, so that's our question that we're asking. We're going to have 2. The first one we want to be specifically this, and the second one we want to be specifically this. So if we draw the Punnett square for this, we know that from this parent, if we put its gametes on the side and we put this one up here on the top, if I just quickly fill in this Punnett square, these are the possibilities that we have. So if we were to take this idea and answer this question here, the chance that the first offspring is going to be big A, if you just look here, it's 1 out of 4. So that would be the probability for that one. And then if we look at the second offspring, which is an independent event, meaning it doesn't really matter what we had the first time, the second time, this offspring has a 50% or a 1/2 chance of being heterozygous. So if we want to get this and this, we just simply take the 2, we multiply them together, and we get an overall probability of 1/8. Okay, so very similar to the boy-girl example, but now we're just taking that same concept and we're looking for specific genotypes here. We could also ask the question looking at specific phenotypes. So let's take a look at that. Okay, so if we were to assign some looks to this, perhaps big A is going to be tall and little a is going to be short. Okay, so we might say, what is the probability that the first 2 offspring are tall and then the third offspring is short? Okay, so notice that one aspect here is that we're giving a specific order for this. So we want the first one to be tall. We want the second one to also be tall. And then the third one, we want to know the probability that it's going to be short. And we want all of these things to happen. So that's why we're going to use this multiplication rule. So if we look at that, notice that if we just look at our Punnett square and we assign the phenotypes, from these 2 parents, 3/4 of them are tall. and 1/4 of them would be short. So having that in front of us makes it easy to kind of answer these individual probabilities that we see at the bottom. Because when we look at the first child, the probability that it's going to be tall is going to be 3/4, because we count up 3 out of the 4 boxes that have that. Then when we look at the second child, it's an independent event, and that one's going to be 3/4 as well. And then when we get to the third one, again, we evaluate it independently, and that one's going to be 1/4. So if you take these and you multiply them all together here, we're going to get 9 over 64. So that would be our probability that our first 2 offspring are going to be tall, and then that third offspring is going to be short.